Okay, guys, learning target number 5. So it says I can use the following continuing motion equations. So let's take a moment and let's look at those. Some of these we've seen before. Displacement, okay, what's a change in position, right? And then we also came up with this equation when we were looking at a position versus time graph, and we were looking at that line there, and we came up with an equation of that line. And then we know that average velocity is a change in position over a change in time. Average acceleration is a change in velocity over a change in time. We're going to look at how we can go from this and end with that. Then we'll talk through how to apply this equation as well as that one. Okay, so a lot of this learning target, as we finish up this unit, it's doing practice problems and listing what we know and what we don't know and drawing out the problem. So here's what you're going to see a lot of. First, it's going to be draw a picture of the situation. Then it's going to be establish an origin. From there, it's listing your knowns and unknowns, and then picking which equation you're using to find your final answer here. Okay. Now, these continuing motion equations work in an inertial reference frame, meaning that see if our carriage is standing still, something, a drop of water falls straight into the bucket, and the smoke from the candle rises straight up, and when we throw a ball, we kind of see this parabolic motion, okay? But if our carriage has some form of acceleration, then the drop no longer lands in the bucket, and the smoke comes off to the side. We see that our light kind of tips, and then we don't have this parabolic motion. It kind of comes back onto us. And then something that was stationary before starts rolling. Now, another form where we have this same type of reference frame is when our velocity is uniform, when we don't have acceleration, but we're moving at a constant velocity. When that's the case, we get the same situation as if we were standing still. The drop falls straight into the bucket, the ball stays where it's at, we have parabolic motion, those kinds of things. Okay, so these equations work here and they work here. Now, we also have to recognize relative motion. Okay, so an example of this, if we have a car traveling west at 30 miles per hour and a car traveling east at 60 miles per hour, what's the relative velocity of both vehicles? So we have car A traveling west. Okay, so here's our vehicle A, and we're traveling west at 30 miles per hour. Okay, and then you have car B traveling east at 60 miles per hour. Okay, so what is the relative velocity of both vehicles with respect to each other? Meaning, if I'm sitting in car B and I'm moving at this constant velocity, if I'm here, how fast does it appear to me that A is approaching? Because if I was stationary, if car B was stationary, we'd say that car A was approaching at 30 miles per hour, but that's not the case. Car B is not stationary, it's moving at a constant velocity of 60 miles per hour. And so from this reference frame, looking at car A approaching, car B would say that A is approaching at 90 miles per hour. Same for A, right? Our 60 plus this 30. If I'm here moving at a constant velocity and I see B approaching, it's not approaching at 60 miles per hour. Someone standing on the sidewalk says that it's approaching at 60 miles per hour, but me in the vehicle, I say that car B is approaching at 90 miles per hour as well. So that's what we mean by a relative frame of reference. All right, so now, before we had our average velocity equation. And a lot of the times we find it helpful to solve for the final velocity of an object that has some average acceleration. So that's what we're going to do. We're going to rearrange this equation so that we're solving for velocity final. Okay? So a couple of things you should keep in mind. First, delta V is velocity final minus velocity initial. And then delta T is T final minus T initial. For the vast majority of problems, T initial is just 0, right? Like we say, my speed went from this to this, and that happened in 5 seconds. Well, that 5 seconds is time final, and time initial is just 0, that moment we started making these observations. Okay, so in most situations, I would say that our time initial is 0. So if that's the case, I'd say acceleration is velocity final minus velocity initial divided by time final. And if it's our only time component, we could just call it time, right? 5 seconds or whatever. Now let's solve for velocity final. Well, we have this t component in the denominator here. And so let's get that into the numerator. So like we're going to times by t times by t. Okay. So now we have acceleration times by t is equal to velocity final minus velocity initial. But we want to know what velocity final is all by itself. So we're going to add velocity initial to both sides of the equation here. Okay. And so we have velocity final is equal to velocity initial plus acceleration times by time. And remember, this is an average acceleration. Okay. And see, we just solved for that equation. Right there, we just figured that equation out. Okay. So we're going to use that equation quite a bit. Let's keep going though. Okay. The golf ball rolls up a hill towards a miniature golf hole. Assume the direction towards the hole is positive. If the golf ball starts at the speed of 2 meters per second and slows at a constant rate of 0.5 meters per second squared, what is the velocity after 2 seconds? All right. Draw a picture, establish an origin. Okay. So a golf ball rolls up a hill in miniature golf. And so we have golf ball rolling up the hill, and right at the top of the hill, that's where the hole is. Okay, so there's our golf ball. And we're going to assume that the direction of the hole is positive, so we're going to call this positive. Okay, so we drew our picture. Now let's establish our origin. Let's say this moment that we hit that golf ball to have it go up the hill, that's going to be our origin. That's our 0, 0 point. Okay. So we drew a picture, we established the origin. Now let's list our knowns and our unknowns. So let's see. If a golf ball starts with a speed of 2 meters per second, okay, again, speed, but we're going in the positive direction. So velocity initial will be a positive 2 meters per second. And slows at a constant rate of 0.5 meters per second squared. Meters per second squared, that's acceleration. Okay. But we have positive acceleration, but it's slowing down. When our velocity is positive and we're slowing down, our acceleration has to be negative. So it's accelerating at a negative 0.5 meters per second squared. What is the velocity after 2 seconds? And so time is going to equal 2 seconds. And what we want to know is this velocity after that time's occurred. So velocity final, that's what we want to know. And we just rearranged this great equation. We said that velocity final is going to equal velocity initial plus acceleration times by t. Or velocity final is going to equal velocity initial, which is 2.0 meters per second, plus acceleration, which is negative 0.50 meters per second squared, times by time, which is 2 seconds. Okay? Now, let's do a unit analysis. Let's see, does this actually give me a final velocity, which would be in meters per second? So I have meters per second plus, and whatever units we add this to, right? It has to be meters per second or this doesn't work, because we can't add or subtract values that have different units. So let's look at this meters per second squared timed by seconds. So we have meters per second squared multiplied by seconds. Put that over 1. So that seconds cancels with one of those. So I'm left with meters per second. So that's the units right here. And then we're adding that to meters per second, which just means we end with meters per second. That's exactly what we wanted. Okay, good. Means we rearrange that equation correctly. Now, let's start plugging these values in. So we have 0.5 times by 2.0. Okay, so we have velocity final is equal to 2.0 meters per second plus a negative 1 meters per second, because I just did the 0.5 times by 2, but we had that negative there. Okay, and so then 2, sorry, we had 2 sig figs, we're going to end with 2 sig figs, 2 meters per second plus a negative 1 meter per second, because our final velocity is going to equal a positive 1 meter per second. Right, now, part B. What is the golf ball's velocity if the constant acceleration continued for 6 seconds? Okay, so now what we're saying here, this situation has changed a little bit. We're saying we're no longer wondering what the final velocity is for 2 seconds, we're wondering what it is for 6 seconds. So what is the golf ball's velocity if the constant acceleration continued for 6 seconds? Okay. So velocity final would equal my same initial plus my same acceleration, but now it's multiplied by 6 seconds instead of the 2 seconds. Okay, so this would be 2.0 meters per second plus a negative 3 meters per second. So my final velocity would be negative 1.0 meters per second. Okay, so it essentially means, like, let's say this hole wasn't there and we continued up the hill. After some time, we start rolling back down, we'd have a negative velocity, and after 6 seconds, we'd see that negative velocity at 1 meter per second speed. Okay, so here's the next equation that we're going to start working with. So take a moment and read through this and make sure you're understanding what each component is. Then we're also going to look at this equation. And then once we have those two, we're going to do a few examples using those equations. We're not going to derive these ones. These ones are just provided to us. If we had our wonderful calculus skills, ready to go in place, we'd derive them. But that's not a prerequisite for this class. So this is one of those situations where it's like, here's the equation that works, and now let's use it in these following situations.